Hello, this is Professor Arlo Kane, Department of Mathematics and Statistics at Cal Poly Pomona. This is a short screencast on constructing harmonic conjugate points using GeoGebra. This is part of my course on projective geometry, and the construction that we want to automate in GeoGebra is given three distinct collinear points A, B, and C. We want to construct a fourth point F such that A, B, C, and F are harmonically related, meaning in particular that F is the harmonic conjugate of C with respect to the points A and B. The method for doing this is to construct a quadrangle having A and B as diagonal points and one of its sides passing through the point C. Then F is the meeting point of the opposite side of that quadrangle with the line AB. We construct that quadrangle in stages by first plotting a random point P, not on the line through A and B, then drawing a point Q on the line from between A and P, and then connecting P to B, B to Q, and P to C to form three more sides of the quadrangle. The meeting point of PC and BQ is a third point of our quadrangle, R, and when we connect R to A, we'll determine another side. The meeting point of AR and PB is a fourth point of the quadrangle that we call S, and the side from Q to S of the quadrangle is opposite the side between P and R, which passes through the point C. Therefore, the meeting point of our side QS with the line through A and B is the point F that we were trying to construct. In the course, we proved from the axioms of geometry that the point F is uniquely determined by the points A, B, and C. And what that means in practice is that this construction is completely independent of the choice of P. Notice that as I vary the choice of P, or the choice of Q on that line for that matter, the point F does not change at all. The only way to move F is to change one of the input parameters, like its conjugate point C, or the points A and B that the conjugation is taking place with respect to. Now the process for constructing F involved building that other quadrangle, P, Q, R, and S, which involves a lot of steps, a lot of mouse clicks, and if we had carried it out using pencil and paper and a ruler, it would have also had the possibility for a lot of errors. We'd like to build a tool in GeoGebra which allows us to click on three collinear points A, B, and C and have the fourth point F harmonically related to A, B, and C be automatically determined. We will use this tool to explore the harmonic net generated by A, which is 0, 0 in the plane, B, which is 1/2 0, and C, which is 1, 0. And to program the construction, we need to understand that the computer can't take an instruction of choose a random point P not on a line. You have to give it a specific one. And choosing a point Q on the line AP distinct from A and P is again not a instruction that the computer can follow. We have to specify the choice of Q. Then we can create a custom tool in GeoGebra to encode that construction. Okay, so here we are in GeoGebra. We're going to use the input bar down here at the base of the screen to enter our points A and B and C with those specific coordinates that we want to investigate. A equals 0, 0. B equals 1/2, 0. And C equals 1, 0. You'll see that at the scale I've got this set up at, those points are relatively close together. We can zoom in using the zoom in tool in order to show the points a little bit more clearly, and we can use the move graphics view command to put them in the center of the screen. Next, let's go ahead and use the line tool to construct the line through A and B, which of course is just the horizontal axis. We'll need the line in our data in order to intersect it with other lines in the construction to determine our point D harmonically related to C with respect to A and B. The next step will be to choose the points P and Q, not on this line, such that A, P, and Q are collinear. We need to be specific about this because the computer is going to execute our instructions as a program. So we're going to give it a very particular choice of P and Q for this investigation. What I'm going to do is use the circle tool, centered at A, passing through B, and I'll also construct the circle centered at B, passing through A, and then I will intersect these in order to determine points not on the line through A and B. We're going to rename this point E to be Q, and construct the line through A and Q, and use the midpoint of that line as the point P. Now that I've determined the points P and Q, these circles are really irrelevant, so I'm just going to hide them. And we'll see that, and also this auxiliary point D that showed up when I intersected the circles. And we'll see now that A, P, and Q and the line through A and P is given as we had before. So I just need to now follow the steps of the construction to connect these points to the other sides and form that quadrangle. Okay, so here I've skipped ahead a few steps, connecting P and B, connecting Q and B so that B becomes a diagonal point of our quadrangle, and connecting P and C to ensure that that is one of the sides of our quadrangle. And then where that line PC met QB, I constructed the point of intersection R using the intersect two objects tool. Then I joined R and A to form another side of our quadrangle, and where AR meets PB, I need to construct a point of intersection. So again, I use the intersect objects tool, clicking on the line PB and the line AR, determining a new point, which we're going to rename as S. Then the line through Q and S meets our line through A and B at the conjugate point, which we had called F before, but we're now going to call D. Notice that when I renamed that point as D, the other point that had previously been called D got renamed automatically as D sub 1. We're not ever going to use that other point, so it's sort of extra information anyway. And this is a nice feature of GeoGebra, that it won't doubly name objects so that you would get confused. One thing to notice in the algebra view on the left is a color coding of the various points and lines. Notice that the points A, B, and C are colored in blue, while all of the other information is colored in black. This is illustrating that the black information is completely dependent on the data of A, B, and C. That's what we want. We want to tell the computer eventually, start with 3 points and determine all of this other stuff, in particular finishing with the point D. Now we'll go ahead and create a custom tool that encodes all of that construction. Up in the Tools menu, we'll click on Create New Tool. Brings up a menu asking us first for the output object of this tool. That's the point D. So we'll scroll down here and select it. Next, it'll ask us for the input objects. And notice it's already grabbed the input objects that we noticed in the algebra view, A, B, and C. If those weren't in the list when you did this construction, you would click on this menu and scroll down and find them in order to add them into the list. Next, we'll give the tool a name. I'm going to call it H of A, B, C, D, and click on Finish. It says we've created a new tool, and you'll notice that up in the input in the toolbar there's a new icon for that tool. Let's go ahead and hide all of the stuff in the construction other than the 3 blue points that we started with and the 4th point D that was produced by the construction. So that means we'll hide S, R, Q, P, and all of the lines. So now suppose that we wanted to investigate what the harmonic conjugate point of B was with respect to A and D. Our new tool gives us that capability. We start with clicking on A, D, and then the point we want to conjugate, B, and it produces automatically the conjugate point E. Similarly, if we wanted to investigate what the harmonic conjugate of A was with respect to B and C, we would first click on B and C, the base points of conjugation, then the point A we want to conjugate, and our tool would determine its harmonic conjugate point F. Your assignment is to use this custom tool you've created to generate points that are harmonically related to one another and investigate the nature of the harmonic net generated by A, B, and C. Something interesting to note for this particular choice of A, B, and C, which on the number line represented 0, 1/2, and 1, the first harmonic conjugate point we created, which was the conjugate of 1 with respect to 0 and 1/2, turned out to be 1/3. Next harmonic conjugate point we constructed was E, turned out to be 1/4. If I did the harmonic conjugate of D with respect to A and E, we'll notice that the point we constructed, G, is 1/5. That's an interesting sequence. 1, 1/2, 1/3, 1/4, 1/5. We're getting the unit fractions between 0 and 1 by this process. But along the way, we also investigated the harmonic conjugate of A with respect to B and C, obtaining the point F. F, you'll notice here, corresponds on the number line to 2/3. Not a unit fraction, but a fraction nonetheless. Your goal is to use this new tool to construct a bunch of points which are harmonically related to A, B, and C, and thus explore the harmonic net generated by A, B, and C on the number line.